base scheme S. I'm going to suppose affine and no theory. So we've been talking about finite commutative group schemes over a field. And a lot of the stuff that I said there remains true if you're over S, at least if you consider finite flat group schemes. So we're going to consider finite flat. So we didn't need to say flat before because we were over a field. Now it's really important that we say flat. So finite flat commutative group schemes over S. So whenever I say group scheme over S, I'm going to mean finite flat. Okay, so I'm just going to quickly say a bunch of things that are true. We already talked about it in more detail over a field. Okay, so these groups correspond to Hopf algebras over R. And you get the ones which are finite and flat, the Hopf algebras which are finite and flat. When you're over an Euclidean ring, a finite flat module is projective. So these correspond to Hopf algebras over R, which are finitely generated projective R modules. And of course, you want commutative and co-commutative in there. So you can again define the order of such a group scheme. Remember before we defined it as the dimension over the field of the coordinate ring. Here we define the order as the rank of the Hopf algebra. Now the rank of a projective module sort of makes sense. It's a locally constant function of the base. So this is really, you can think of it as a number if the base scheme is connected. We're only going to be dealing with the case where S is local anyway, so I'll just think of it as a number. Okay, quotients work as they should. If you have a closed subgroup scheme, and they're both finite and flat, then again, G mod H exists, and it's finite and flat. You have the correct order, the order you'd expect. All right, you can again classify the Étale group schemes. It's very similar to before, but uses more advanced terminology. There's an equivalence of categories between the finite Étale commutative group schemes for S and the category of finite modules for pi 1. So here this little s is the geometric point of S. Oh, and this is in the case where S is connected. Okay, so if S were a field, if R were a field, then this pi 1 would just be the absolute Galois group. This is what we said before. The Étale group schemes over a field correspond to modules for the Galois group. And generally you have to use pi 1. If you don't know, this is the Étale pi 1. If you don't know what that is, this is actually more or less a definition. The Étale pi 1 is basically defined as being so this is true. But one case where I can say something that's not sort of tautological and still interesting, if R is the ring of integers and an extension of QP, then this pi 1 is the unramified Galois group. So in this case, you get representations of the Galois group which are unramified. Okay, if we assume that R is local and tenselian, or I mean local and complete if you want, complete implies tenselian, then you get a connected Étale sequence still. So if we have G is spec A, where A is our Hopf algebra, it's an R module. So A is semi-local since R is tenselian, it's going to break up into a product of local things. And you can define the connected component of the identity is just going to be spec of A0 like before. Where A0 is the thing where the co-unit factors through. So previously I defined the Étale quotient completely incorrectly, and no one called me out on it. So I said that this thing has a maximal tau subalgebra and the tau quotient respect of that. Well, I mean, when you have nilpotence, there's not a unique maximal tau subalgebra. There's no way to define that. But there is a unique one that's stable under co-multiplication. And that gives you the tau quotient. So it may be easier just to define the tau quotient as G mod G0. Okay, but whatever, it exists. This is the maximal tau quotient. You have that connected to the tau scale. So Cartier duality works. So that shouldn't be surprising. Everything we said was pretty formal. I mean, all you needed. So the way Cartier duality works is by taking the R linear dual of A. If we're dealing with something that's projective, projective modules, doing the R linear dual is a nice operation. And all we needed was that operation was, contravariant in respect to tensor products when we're working over a field to figure out everything about Cartier duality, and all that holds true here. So everything works as you'd expect with Cartier duality. Cartier duality is okay. All right, so these are the general facts that we need. Are there any questions about this setting? All right, so the main thing that I want to try to do today is Raynaud's theorem. I don't know if we'll have time to get through it, but we'll see how far we get. So let me begin by stating it for you. So basically for the rest of today, I'm going to have K as a finite extension of QP. R is going to be the ring of integers in here. E is going to be the ramification index. In the absolute one, the ramification index of K over QP. And little k is going to be the residue field. So Raynaud's theorem is the following. It says, okay, so this only applies in the setting where the ramification index is less than p minus 1. Okay. And it says that if you have two finite flat group schemes, finite flat commutative group schemes over R, and they're isomorphic over K, which are isomorphic over K, then they're isomorphic over R. So in other words, if you thought about starting over K, it says that as you can extend to R, you can extend to R in a unique way. When you're in this setting of small ramification. So remark, this is false if E is not less than p minus 1. Does anyone see an example?
Mu p something.
Yeah. So if you take K to be the field adjoining the P through community, then obviously the constant scheme Z mod PZ and UP, and you have these two group schemes, they're finite flat group schemes over R. They just make sense absolutely over Z. And they're going to be isomorphic over K because you have a P through community. But they're not isomorphic over R, right? I mean, their special fibers are different because one's a tau and one's connected. So it's very easy to have a counterexample as soon as you have this large ramification index. But all right, so we're going to try to prove this theorem today.
So is it true that arbitrary maps within group schemes extend as well? Or?
Yeah, it's a fully faithful functor if you want the generic fiber. And you can deduce that from this theorem. Okay, so the outline of the proof of this theorem, very coarsely, is we're going to first show that it's enough to prove it when the groups involved are simple, meaning their generic fibers are simple. And then we're going to classify all the simple ones. And then we're just going to check by hand using the classification that it's true for simple things. So the hardest part is going to be that second step, classifying the simple ones. But I'm going to start by showing how you reduce to the simple case. So prolongations. Let's start by discussing prolongations. So a prolongation, so suppose we start with G0 over K. So a prolongation is just G over R with generic fiber G0. Just an extension over R. That's just the word I'm going to use. If you look at Tate's articles, it's the word that he uses. So if we write G0 equals spec A0, so A0 is a finite dimensional K algebra. Then a prolongation G we can write as spec A, where A is going to be a subalgebra. It's an R subalgebra. So it's just kind of a lattice in this vector space. And in fact, the prolongations of G0 correspond bijectively to the R subalgebras A inside A0, which are, they're lattices, so which are finitely generated over R, which span A0 over K, and are closed under co-multiplication. So you can think purely in terms of rings if you want, and then prolongations are just these kind of lattices inside A0. And so you can show that these conditions imply that A is automatically closed into the antipode map. So you can just forget about that.
Sorry.
Yeah.
Is it obvious that there is a prolongation?
No, it
Okay.
doesn't have to be. So I'm going to partially order the prolongations just by thinking about algebras. Just to use inclusion. So one's bigger than the other if you have a continuum of the rings. So there's a partial order to the set of prolongations. And the first little proposition is that any two prolongations of G naught have an infimum and supremum. I mean that in the sense of partially ordered set, the smallest thing bigger than both of them. And here's the proof. Okay, so I'll use the word prolongation for the algebras as well as the group. So suppose that A and A prime are prolongations. So the inf is supposed to be the smallest thing bigger. Bigger means you have a containment of rings. So that's the supremum. So the supremum has to be a subring containing both A and A prime. So the sub had better contain A prime, right? It has to contain that. This is a subring by definition, and since co-multiplication is an algebra homomorphism, it's easy to see that this is closed under co-multiplication. So these are equal. So that's obvious, and A prime closed under co-multiplication. So this shows that the supremum exists, and that the infimum exists by Cartesianity. So I'll elaborate on that remark a little. The point is that the prolongations of G, G naught, are in bijection with the prolongations of the dual G by Cartesian duality. And this is order reversing. So we have these two posets. One corresponding to G naught and one corresponding to its dual. And these two posets are opposite to each other. So that means whatever general fact you prove about the structure of this poset is going to be symmetrical. Okay, so if you prove that you always have infimums, then you of course always have supremums. What do you mean by intersection?
Taking if you want to taking intersection of any of them.
Oh, I'm not sure, I don't think so. Okay, I don't know the answer.
Those finite generation.
Hmm?
The finite generation feature.
Well, everything's in the theory, so I don't think that's going to be a problem. Maybe that's, I'm not sure. Okay, and the next proposition is that if you assume if G does have a prolongation, G naught has a prolongation, then it has a maximal one and a minimal one. And the proof, so remember G naught is spec of A naught. And A naught is a finite tau K algebra. That means it's the product of finite extensions of K. So it has a maximal order. Just the product of the ring of integers in those fields. So that means that if A is a prolongation, then A is contained in this maximal order. I mean, the quotient has finite length. There's not much room between these two things because they're both lattices in the same vector space. So this shows that the prolongation satisfies the ascending chain condition. And that together with having supremums says that you have a maximum. And then of course minimums come from Cartesian duality. So I'm going to introduce a term just to make life a little easier. I'm going to say that G naught satisfies property UE, meaning unique extension. Maybe I should call it UP for unique prolongation. If any two prolongations are isomorphic. So Raynaud's theorem just says that everything satisfies this property if you have small ramification. And what we can say from this, so maybe I'll call the maximal one G plus and the minimal one G minus, that G naught satisfies UP if and only if so there's a natural map. So the ring for G plus is supposed to be bigger than the ring for G minus. So there's a map the other way. So if and only if this map is an isomorphism. Right, it means saying that you have UP means this poset of prolongations has one element. That's the same as saying the maximal and the minimal are just the same. And this is nice because we don't have to like kind of think of arbitrary prolongations out there. We just have these two canonical ones that we have to check are the same. So for instance, this shows that you can check that G naught satisfies UP by going up to an extension. If you want this to be an isomorphism, you can check that by going up to an extension. So up here, everything's isomorphic. Okay, so suppose now we have a short exact sequence over the generic fiber. And we have a prolongation G, G0. then you can make a prolongation of G0 prime by taking its scheme theoretic closure in G. So I'll leave that for you to check. So G prime, the scheme theoretic closure, G0 prime in G is a prolongation. And then you can get a prolongation for the quotient by taking the quotients of the prolongation. So when you have one in the middle, you can build one on the outer ones like this. Yeah. I mean, you shouldn't, it's best not to maybe think about these things too abstractly. Think of them as lattices in the ring.
Oh, right, they have a soup. Oh, yeah,
Yeah,
sorry,
yeah.
Okay.
I confuse myself with that sometimes. It's much more clarifying to
Yeah.
just think inside of one ring. Right, so if you have one here, you get one on the edges. And now it's easy to see that if you have a second one for G0, which is comparable to G, so suppose that H is a second prolongation, you have a map like this. Then you get maps on the other ones as well. So you have G prime maps to H prime, and G double prime maps to H double prime. And so we have this commutative diagram of exact sequences. And so we can say if the outer two maps are isomorphisms in the middle ones. And so this shows, to prove this proposition, if the outer two guys, G0 prime and G0 double prime, satisfy UP, and so does G0. Right, you take G and H to be the maximal and minimal prolongations, and then G prime and H prime are automatically isomorphic because G0 prime satisfies UP, and these two are automatically isomorphic, so you get an isomorphism. So that means that to check UP, we can just concentrate on the case of a simple group scheme. So take G to be the maximal prolongation of G0, and H to be the minimal. So you have this map. So you get maps here and here, right? Now, it may not be the case that G prime is the maximal one for G0 prime, but it is a prolongation. And so you have this map of two prolongations of G0 prime that satisfies UP, it has to be isomorphism. Okay. All right, so we want to understand the simple group schemes over K. And so the first thing I want to talk about is, I mean, if you have a simple object in some abelian category, its endomorphism ring, you can think of it as a modulo over its endomorphism ring, if that thing is commutative. And so I want to kind of elaborate on that idea in the setting of group schemes. So suppose that G0 over K is simple. So it corresponds to this Gauss representation. It's K bar points. This is an irreducible representation of the Gauss defined over P. So I guess I didn't say that, but all the group schemes I'm working with today are P power order. The other ones are at tau. Not really interesting for us. So if this thing's simple in P power order, then this representation is going to, I mean, It's going to be this is going to be an FP vector space. That's a representation of GK. So I'm going to define F to be the ring of endomorphisms of this representation, which commute with GK. So since V is a finite dimensional vector space, this thing is finite dimensional over FP. And since V is simple, it has to be a division algebra. That's just general stuff. And then any division algebra over FP is a field. So this thing is a finite extension of FP. And so you can regard V as an F vector space canonically. And then this representation is F linear, if you want to regard it like that. So V can be regarded, so it is an absolutely irreducible F linear representation of GK. Absolutely irreducible because its endomorphism ring is F. Okay, so now I'm going to assume that our residue field K is algebraically closed. Okay, so that doesn't really fit into the setup I said where our field is a finite extension of QP, but it's okay. You could work with finite extensions of QP unramified if you wanted to, and everything I've said so far continues to go through. Okay, so in this case, this Galois group, GK, is really like the inertia group. There's no unramified part of the Galois group. And you know that it has this sort of wild subgroup, the wild inertia group, and the quotient's the tame Galois group. This thing is pro P. And this thing here is Abeli. So now that there's this standard kind of argument, since this is a pro-P group, the wild part, and it's acting on this, we'll assume to be non-zero FP vector space, it fixes a vector. So the fixed space is non-zero, and it's also a sub-representation of V, since this group IW is normal. So we have this non-zero sub-representation. Since V is zero reducible, it must be the whole thing. And that's to say that the wild inertia group is acting trivially. So that means this representation is really factoring through the tame quotient, which is Abeli. So we can say that V is an absolutely irreducible representation, so I'm thinking of it as over this field F, of the abelian group IT. Of course, absolutely irreducible representations of abelian groups are one-dimensional. So that's just, V is just a one-dimensional vector space in this situation. Because it's a pro-P group acting on something in characteristic P. So it's just some counting thing that it has to fix a vector. It's a standard argument. We can talk about it later. So this motivates a definition. An F module scheme is a group scheme G. And I'm going to allow it to be basically over any base you want, say over K or R. Equipped with the ring homomorphism from F to its endomorphisms. if we say that such a thing is a Raynaud F module scheme, it is an F module scheme such that the order of G is equal to the order of F, which is the same as to say that the dimension over F of G of K bar is 1. And so this discussion I gave preceding this definition proves the following proposition, assuming K is K bar. It says that any simple group over K is a Raynaud F module scheme. For some F. And we saw F for endomorphisms of the Gauss representations. Since that's an equivalence of categories between group C's and Gauss representations, you can move the S back to the group C. So this is our first step to sort of classifying the simple groups. They all are sort of one-dimensional F module schemes. And result of this proposition, we can say the following. If all, let me phrase it like this, if all Raynaud F module schemes over K unramified, the maximal unramified extension of K, satisfy UP, then all groups over K satisfy UP. And there's nothing to this beyond what I've already said. Let me just say verbally what happens. You have a group over K, you want to check that it satisfies UP. You can check that by first passing to the unramified extension. You just have to check the map from G plus G minus to nice minus. And then you can use what we proved to break it up into simple things. And you suffice to check the simple ones. And then we just proved that the simple ones are all these Raynaud F module schemes. That's it. All right, does this make sense? Okay. So for the rest of the time, we're going to concentrate on these Raynaud F module schemes and try to say as much as we can about them. All right, so we want to understand these F module schemes now. So for the rest of the day, the setup is going to be the following. So we're going to fix our F. This is a finite field size Q, which is QVR. And we're not going to need to assume that K, little k is algebraically closed, but we need to assume that there exists an embedding of F into K. All right, so we're going to need to talk a lot about characters of the multiplicative of F. So some definitions. So a character from F star to R star is called fundamental. Call this chi. If the composition, so F star, R star, and then down to K star, if this thing extends to a field of homomorphism. You extend it by making 0 go to 0. Right? So you want that map to be a field of homomorphism. So two facts. So fundamental characters exist. And if you take any one of them, chi is a fundamental character, then all others are of the form chi to the p to the k. K is some integer.
All
Yeah.
other fundamental characters?
Yes, all other fundamental characters. So it's clear that when you raise to the p power, you still have a fundamental character, because raising to the p power is a field automorphism of k. Right? So those will be fundamental, and they give you all the other ones. So I'm going to enumerate them. So I'm going to write them, but this, okay, so I'm going to call this script I, this index set. So let this be the set of fundamental characters. So I is just some index set that enumerates the fundamental characters. And I'm going to define, so for an element of I, I'm going to define I plus 1 by the equation chi I to the p is chi I plus 1. This defines I plus 1. So in other words, this I, it makes sense to talk about the next element. And you can get all elements by starting with one element and going around. And in fact, this makes I into a Z mod of R, of course. But remember, Q is P to the R. So if you have any other character, then you can express it in terms of fundamental characters. So there exists a unique expression. Mu is the product over our index set of the fundamental character, some power, which I'm going to call U of I. This isn't great notation, but so where mu of I is an integer, and it's between 0 and p minus 1, and not all the mu i's are 0. And the basic idea is that the group of characters is cyclic. So if you have some character and a fundamental character, you can write it as some power of the fundamental character. And then you just take that power and express that with a p-adic expansion. And that gives you these other ones. So the trivial character, use the trivial character. I mean, you'd like to write that as the product of chi i's to the 0, but I'm disallowing it. It's the product of the chi i's each to the p minus 1. Okay, so now that that's out of the way, let's start talking about Raynaud schemas. All right, so let's say that G equals spec A is a Raynaud F scheme over R. So we want to like completely understand the structure of A. Like we're going to try and write it in terms of generators and relations and say everything we can say about it. So the way that we're going to go about analyzing this, the group F star acts on A, right? And we're going to decompose the ring under that action and get a bunch of eigenspaces and then look at how they work. So first of all, A decomposes as R plus I, for I is the augmentation angle. And this thing is stable by the action of F. So this group F star acts on I. And so there's a finite group acting on I, the order of this group is Q minus 1. That's invertible in our ring R. So we can decompose into irreducibles. And because we assume that the residue field contained an embedding of F, all the irreducibles of F star are just one-dimensional characters, because all the characters kind of exist over R. So this decomposes as the sum over the characters of F star of, say, I mu, where I mu is just a set of elements of I, such that Tx on x gives you Ux, U of Tx. So here I'm going to write T for the map of A induced by T in that. That's sort of the F module structure. It's given by this map of Hopf algebras. So if we go over K bar, so this G over K bar is an F module scheme over K bar of dimension 1 over F. So it just has to be the constant F scheme, constant group scheme on F. Constant group scheme on F. And the ring corresponding to that thing is the algebra of functions from F to K bar. So that means we have an isomorphism, and we have to pick this isomorphism, but we're going to pick it once and for all, of AK bar with the ring of functions. 1F taking values of K bar. And in particular, this means we can regard characters of F as elements of AK bar. So for a character mu, taking values in K bar, I'm going to write epsilon of mu for the function on F, which is 0 at 0 and extend mu. This extends mu by 0. And we can regard this thing as an element of A K bar under this identification. So it's pretty clear that if we look at this eigenspace, I mu, at least over K bar, this is just spanned by this guy epsilon mu. Right, I mean, epsilon mu clearly transforms under the action of F by mu, and it's pretty clearly the only thing. So this implies that I mu is rank 1 over R for all mu. And I'm going to pick a generator, xi. This is a generator of this I mu, where mu is the fundamental character of I. So it's a generator of this as an R module. So these are going to be the things that generate our ring. And this is kind of how we find the generators. And we have to prove that these xi generate as an algebra. That's what our kind of goal is, prove that these things generate. So there's a lot of notation going on. There's going to be more to come. So let me take just a quick pause. Does anyone have any questions about what's going on so far? It's really complicated in terms of notation and what I've written, but it's not very complicated in terms of the idea. We just decompose I, and we pick some elements in these eigenspaces. Okay. So for a character mu, which decomposes like this, is just notation. I'm going to define x superscript mu to be the product of the xi's with the same superscripts. So to show that these xi generate as an algebra, it's equivalent to showing that these x mu's span as a module. I want them to span the ideal I. So the way that we're going to do this is x mu span some sub-R algebra of I. We want to show it the full thing. So we're going to do a similar construction in the Cartier dual and get some things that span an R submodule of the augmentation ideal there. And then we're going to show that those two submodules are actually dual to each other. right? And then that means that they have to be the whole thing. Because normally if you take a sub-thing and its dual, it should be bigger than the dual of the other thing. When they match up, it's going to force inequality. Okay, so now we're going to kind of do the similar picture in the Cartesial side. So I'm going to let B be the Cartesian rule of A. So when we tensored A up to K bar, we got the functions on F. So when we tensor B up to K bar, we get the group algebra. So we know that those two things are dual. So there's a natural isomorphism of B K bar with the group algebra of F. And for an element of F, an element T of F, I'm going to write this T for the element of the group algebra. So I'm going to let J be the augmentation ideal. And as I said, this is going to decompose into J mu's, sum over the characters of F star. So again, when we tensor up to K bar, we can give generators to this J mu, kind of obvious ones by looking at the group algebra. So they go, it's a little different though. So if mu is not the trivial character, then J mu tensored up to K bar is spanned by what I'll call E sub mu, which is the following thing. So you sum over the elements of F star, you do U inverse, and then this element of the group algebra. So I think it's pretty clear. If I act by an element of F star on this, say some element S, I'm just going to be putting S's in front of all these T's, and then I can divide them out, and I'm going to get a mu of S coming out. So this thing is a mu eigenvector under the action of F star. And it does live in the augmentation ideal, right? Because the augmentation ideal are the things where the coefficients sum to 0, which is the case if you have a non-trivial character. So if mu is equal to 1, then this thing is spanned by what I'll call E of 1. And we can't do quite the same definition, because if we put the trivial character here, this wouldn't be in the augmentation ideal. Because the co-unit on this thing sends all these guys to 1, and you would just get 1 instead of 0. So it's off by 1 from being 0, so we just subtract 1. Minus 1. So IK bar and JK bar are dual vector spaces. And we have bases of each, the epsilons and the e's, and they're dual bases. That's why you want to include these 1 over q minus 1, so get the parents come out to be 1. So that's a little computation that you can do. So I'm going to define yi to be sort of similar to what we had as xi. Oh, I didn't say this. So xi, remember, so xi was a generator for our i's of chi I. And over k bar, we said that this thing was just generated by epsilons of chi I. So that means I can write xi as some constant multiple of that guy. I'll just write epsilon I. So epsilon I means epsilons of chi I. So this thing is some multiple of that, where ci is some element of k bar star. So I'm going to define yi to be ci inverse times ei, or again, ei, e sub chi I. And so these are our candidate generators for B. It's an algebra. So once again, I'm going to define y to the mu to be the product of the yi's to the mui's. We want to show that these things are a basis for the dual algebra. Okay, so I'm going to define W sub mu, this is lowercase w, to be the inner product, the pairing of this x mu with y mu. These things are living in dual vector spaces. This is just the pairing between the two spaces. And now if you remember the definitions of these things, these were defined as the sort of products over the xi's and the yi's with the correct exponents. So this is equal to the product of xi to the mu I, and the xi was the ci times epsilon I. And my mu was defined sort of similarly. So ci inverse ei in mu I. And so these c's are just scalars. They pull out of the inner product, and they exactly cancel with each other. This is just equal to the product of what you would call epsilon to the mu and e to the mu. And this thing is just this product. And the thing that's noteworthy about this expression is that it's completely independent of g. This is just some number that we've defined straight from the group algebras. Does everyone know what I mean? Yes? No? No? Did you say no?
Not really.
Okay, so let me emphasize this because this is a very important point. So AK bar is functions from F to K bar. And DK bar is the group algebra. K bar joins F. And these elements, epsilon of mu and E of mu, we just define kind of straight in here. So epsilon I was just the character chi I regarded as a function. And EI we defined as just something like 1 over q minus 1 sum of chi I of t times t. Right, so we're just kind of, you can think of this as just starting with F and then defining these two algebras, and then we're defining these two elements. Okay, all we're referring to is the group structure, the field structure on F, nothing else. And then this E mu was just the product of EI's to the mu i's, it's just a notational device. And so this pairing is some element of K bar. It's just it's just the pairing of these things. It's just that element of K bar. It's defined purely just in terms of that. This expression for it, in fact, shows that it's an R because these are in R dual algebras. Okay, so that's what this W mu is. It's just an absolute constant. And then we'll also define W of I to be the pairing of xi to the p power with yi to the p power. And similarly, when you write this out, this just comes out to be the pairing of epsilon of I to the p power and e to the p power. So again, it's also just an absolute constant. So I think it's fair to say that the main work in doing what we want to do is computing these numbers, or at least the first part of their p-adic expansion. So maybe, I plan to do that computation just now. Maybe let me state that computation and say what we get from it. I think that'll be clearer. So the result is the following. W of mu, well, actually the exact number doesn't even matter, but I'll tell you what it is. So W of mu is just the product of the mu I factorials mod p. And Wi is equal to minus p mod p squared. Okay, so I'll try to prove these today, but let me first say how they're used. So first of all, remember these mu i's are all strictly less than p. They're allowed to go up to p minus 1 even further. So this thing here is a unit in R. It's a unit in ZP. And that's the pairing between these two things. right? So, I mean, if we look at x mu and say y nu, if nu is not equal to nu, these things are in different eigenspaces, and the pairing is 0. This is 0 if mu is not equal to mu. And it's w mu, which is in r star, if mu is equal to mu. So that says, I mean, we have, here we have I and here we have j, and these things are our dual modules. And then we have submodules of each. The ones spanned by the x mu's and the ones spanned by the y mu's. These are our submodules on each side. And this computation here is showing that they are, in fact, they are duals of each other. The full are duals. And so that means that these inclusions have to be equalities. That's just a linear algebra fact. So this implies that the xi generate A as in our algebra. Now we can say a little bit more. So that only used this first part, that W is unit norm. Now we're going to use the fact that this Wi is p mod p squared to say a little bit more. So if I look at xi and raise it to the p power, remember xi is just some multiple of the ith fundamental character. And I raise the ith fundamental character to the p power, I get the ith plus first one. So this is going to be some multiple delta I of xi plus 1. And similarly on the other side, yi to the p is going to be some multiple gamma of I of yi plus 1. So when I pair xi to the p and yi to the p, these things pull out. I get delta I times gamma I. And the pairing of xj and yj is 1. They were defined in terms of the dual basis. And this is what I defined my wi to be. The wi was equal to this by definition. So this is p mod p squared. Or minus p mod p squared. But whatever, the important part is since both of these are in R, this says that the valuation of delta I is at most E, where E is the valuation of P. And so we've essentially proved this theorem. We haven't done the computations of W's, which we'll come back to. We've shown that A is equal to R of X. It can be presented as follows. R adjoin Xi, mod Xi to the P equals delta of I, Xi plus 1. Where the delta of I's are in R, and their valuation is at most E. Okay, so we've shown that these equations hold in A. But I think it's easy to see that it can't be any smaller quotient because this thing's already finite defined at the right size. I'm not going to go down any further. Okay, so let me just recap. So by decomposing under the action of F star and using these distinguished characters of F star, we picked out distinguished elements Xi of our algebra. And then doing something that I haven't actually done, we showed that they generate as an algebra and satisfy equations like this. So this has given us this presentation for these kinds of group schemes. So the next thing to explain is that the converse of this holds. So let me state that precisely. So suppose that you're given delta i's. So delta of I is in R, and the evaluation of each delta I is at most E. And I'm going to define A to be this thing. And the statement is that there's a unique way to give this a Raynaud F module structure. So there is this unique Raynaud F module structure on A. With the property that the action of an element means that these xi elements are in the chi I eigenstates. That's how we did it before. So t times xi is chi I t xi. And let me explain the proof of this. So I'm going to choose elements Ci and K bar star such that delta of I is equal to Ci to the P divided by Ci also. So if you remember before I was talking about this, I said that my xi was some multiple of my epsilon I, and I called that multiple Ci. Well, if you compute, you find that in our previous notation you have this equality. So now I'm defining Ci's so that this holds. And it's easy to see that you can find such a Ci's. So I'm going to define an isomorphism of AK bar with the space of functions by sending xi to Ci epsilon I. So I'm just kind of reconstructing what we did previously. And again, I'll define x mu to be the product of the xi's and the ui's. Okay, so it's clear that, so the problem, so it's, when we define A like this, it's clear that it's an algebra. We want to find a co-multiplication. That's the real problem. We want to find a co-multiplication. The idea is that we're going to use this isomorphism and try to transfer the co-multiplication back. The hard part is we have to show that this, if we identify A with a subring over here, that's actually closed under co-multiplication. So the way that you can show that something is closed under co-multiplication is to show that its dual is closed under multiplication. And so that's what we're going to do. We're going to consider the Cartier dual, what should be the Cartier dual, and show that it's closed under multiplication. So let B be the R linear dual of A. And of course we have an identification of BK bar with the group algebra. And so I'm going to define, okay, so this x mu, we can write this as, if we use this definition, maybe you think this is an equality, xi is equal to Ci times epsilon I. So this thing is just the product of the Ci's and the ui's times epsilon u. I'm going to define y sub mu to be the dual basis of x mu. And we know what the dual basis of the epsilon mu is. It's given by these e mu's, right? So, so this epsilon upper mu is the same thing as what I was calling epsilon lower mu, actually. So the e lower mu is the dual basis. So to get if we want the dual basis of x, we just have to modify this by these constants out front. So this is just these Ci inverses times e mu. Okay, so I'm going to let yi be just ci inverse ei, as you'd expect, and define y upper mu, like we've been doing, the product of yi's and ui's. And so this, of course, if we use this expression, is the product of the ci's, the minus mui's, times e upper mu. And so when we compare these two things, y mu and y lower mu, right, here we have e upper mu, here we have e lower mu, and the difference between those two things is w mu. So e upper mu is actually just equal to w mu e lower mu, and this is in r star. So that means that y upper mu and lower mu are just off by a unit of r. So they're basically the same thing. So the point is that these y upper mu's span B as an R module. So we can write yi to the p as gamma I times yi plus 1. And just the same formal computation that I did before shows that gamma of I times delta of I is W. And it's just computing over k bar going on here. And now here's the point. This is the point. This thing here has valuation equal to E, because it's P mod P squared. And this thing here, delta of I, we're assuming that its valuation is at most E. So that implies that gamma of I is in R, it's integral. And so this means that yi to the p is in B. B is the span of the y upper mu's. This yi plus 1 is in there. And this thing here is in R. And B contains already, I mean, these y mu's are the monomials in y where the powers are all less than p. So those span B. And now we're saying that when you put in p powers, those are in B as well. So that implies that any monomial in the y is in B. And so that means that B is an algebra. So this means that B is closed under multiplication. And that means that A is closed under co-multiplication. And it's sort of easy to show that, I mean, we had to pick these C's, and then we embedded and showed that A was closed under co-multiplication. That gives us a half-algebra structure on A. You have to worry about, does it depend on the C's because of the other ones? And it's not hard to show that it's unique, but maybe I won't go into this in detail. Okay, so to recap, if we have some sequence delta, where these guys are in R, and they have a valuation at most E, then we can build one of these Raynaud F modules. I'll call it G delta. And this is just spec of R join xi's, y of xi to P, is delta of y of xi. That's sort of what the second theorem I proved said. You can construct one of these things given such deltas. The first theorem said that they were all of this form. So this is very good. It's an extremely explicit classification. It's telling you how to construct your half algebras in terms of very, very simple generators and notations. So here's a simple fact that I'll leave for you to prove. We want to understand the maps between the different G deltas. And there's an obvious way that they should look, and the statement is that that's all of them. So maps F from G delta to G delta prime of F module schemes correspond to sequences AI, where AI is an element of R, And the equation, right? You want AI plus 1 times delta of I to be AI to the p times delta of I. And the correspondence is if you have such a sequence, you build a map. Well, the map on rings sends xi prime to AI times xi. And these are exactly the conditions you need to get those relations to be respected. And the statement is that those are all the maps. Okay, so now we can actually prove something. So suppose E is less than p minus 1. And suppose that we have a map F from G delta to G delta prime. A map of Raynaud F modulus schemes. Such that it's an isomorphism over K. Then it's an isomorphism. Here's the proof. So F corresponds to some sequence of AIs over there, like that. And so we have these equations. So we write it. AI plus 1 delta of I is equal to AI to the p delta of I prime. And so we're just going to show by elementary manipulation that these equations imply that the A's are all units, which is what you need to show that has an isomorphism. So an efficient way to do that, if I such that VI is maximal, V of AI is maximal. And then look at what this equation tells you. So V of AI plus 1 plus V of delta of I is equal to P times V of A of I plus V of delta of I prime. Okay, so on this side, we can certainly forget the valuation of delta I prime. That only makes things smaller. So this is greater than or equal to P times the valuation of AI. And over here, it's less than, well, we know that the valuation of delta of I is less than or equal to E. And the valuation of this guy is at most the valuation of AI, by the way that we chose the AI. So P times the valuation of AI is at most E plus the valuation of EI, which says that P minus 1 times the valuation of AI is at most E. Now, this thing, the valuation of AI, forces it to be 0, right? I mean, if it were 1, we'd get P minus 1 less than or equal to E, but we assume that E is less than P minus 1. So this implies that the valuation of AI is 0, and since that was chosen to be maximal, all the other ones are 0 as well. Okay, so finally we can prove, I mean, again, E is less than P minus 1. If you start with a Raynaud F module scheme over K, it satisfies our UP condition with a unique prolongment, if one exists. So UP really meant any two are isomorphic. And so the proof, well, it's kind of simple. We have to show that this map is an isomorphism. And the point is that if you have a Raynaud F module scheme over K, if you take a prolongment of it, it may not be an F module scheme anymore. I mean, the subalgebra of the Hopf algebra we have may not be stable under the F operations. But it's the maximal and the minimal one will be, because they're unique. And, I mean, the elements of F star are acting by Hopf algebra automorphisms, so they have to preserve those subalgebras. So these guys are necessarily F module schemes over the ring of integers, and this is necessarily a map of F module schemes over the ring of integers. And so then it follows from this proposition. Okay, does anyone have any questions about what we did? Okay, so I've proven everything. I've completely proven Raynaud's theorem, except for these congruences that you need on the W's and Wi's. I have those. I wrote up those to do in lecture. We're out of time now, but people seem kind of lazy-eyed this lecture. There's a lot of notation and stuff, so maybe it's not worth doing that in lecture. I'll put those notes on the web so you can read them. But perhaps it's best just to move on to more exciting things and kind of see how these things are used. So next time we'll start talking about narrow models.